Ravikumar is our final speaker of this afternoon, and he's going to talk about robust estimation via robust gradient estimation.
Thanks, Rob, and thanks to the organizers for inviting me and for this excellent workshop and series of workshops at INI. So I'm going to talk about robust statistical estimation, so a classical problem. And so this is joint work with my students Adarsh Prasad and Arun Sai Sugala, as well as a colleague Shiva Balakrishnan. So here is a typical setup in statistical machine learning, statistical estimation. So first, I try to estimate some functional of some distribution, just given samples from that distribution P. And so in machine learning, we call it the training stage. And this function could also just be some statistical model, some deep neural network model. And then we validate this estimate by some goodness of fit of the estimate to the distribution P, but again, just given samples of this distribution P. So this is called the testing stage. So I have a training stage and a testing stage with respect to the distribution P, but we never see the distribution P, we only see the samples with respect drawn from that P, distribution P. So there's an implicit assumption in this setup, which goes without saying, which is that the samples are not just drawn from P, but are representative of P. And this is actually a much trickier assumption than it sounds. And of course, you could also be in trouble, and the samples could not actually be drawn from P. They could, in actuality, be actually corrupted. Some portion of it could be arbitrarily corrupted, where I can just take some 10% of the samples and replace it with whatever I want, potentially maliciously. So of course, nobody is coming and destroying our data maliciously, but in general, corruptions happen through various mechanisms. And we want to be able to have estimators that are robust to such corruptions. And according to various estimates in what people call data science out in practice, people spend 75% to 80% of their time cleaning the data so that they remove the corruptions, so that the samples that you get are actually representative of some underlying distribution. And so that's the case where the data could actually be corrupted, but even when the data is not actually corrupted, you could still be in trouble. And so this would be the case where the data has long tails. And so you may keep seeing white swans, but there could be black swans in the tails. And the problem in seeing a finite set of samples is that given a very small set of samples, you likely are not going to see many samples from the tails. And so the finite sample could not be representative of the distribution, even though there is no corruption, just because of the long tails. And so that's why this, in fact, in a lot of the standard regularity assumptions imposed on P is that the tails are all reasonable. Right? So it's all buried in page 32, but this is a standard assumption. So what do we do is essentially the question underlying this talk. So here are two, essentially, you can think of these as corruption models or robustness models. So one is a classical Huber contamination model, where the functional that I care about is with respect to some distribution P, but the samples that I'm going to see are with respect to this P epsilon, which is a mixture model between P and some arbitrary distribution Q. I don't want to make any assumptions as to this distribution Q. It could be completely arbitrary. And so this is essentially called epsilon Huber contamination. And even though this P epsilon, you can see that it's mostly P with a little bit of this arbitrary Q thrown in. And so if you look at the TV distance between P epsilon and P, it's at most epsilon, right? It's equal to epsilon. So even though Q is arbitrary. So P epsilon and P are still close, at least in TV, but there is essentially, if epsilon is 0.1, 10% of the data is arbitrarily corrupt, right? So it's a slightly difficult problem. And then the other setting that I talked about is a heavy-tailed model, where the distribution P has long tails, right? So all I might want to assume is that some low-order moments are finite, but nothing more. Right? So these are two settings, and I want my estimators to be robust to these settings. So let's see how existing estimators actually do. So I'm just going to look at a very simple estimator, I guess a statistical model, which is linear regression model. So the x-axis is the size of the model, essentially the number of covariates, right? So 100 through 500, and on the y-axis is just the L2 error of my estimator theta hat. And so the various plots are the different estimators that people have proposed. So the blue one is just OLS, dating back to Gauss, but then people have proposed various other estimators, and Huber himself has proposed essentially using a Huber loss. So that you can see is still not doing very well, right? So at very large p, it's better than OLS, but still not what I would argue to be a pleasant state of affairs, because you can clearly see that the error seems to be increasing with model size. And so this is just 500 variables. If I have 1 million, you can imagine that I can stand on a ladder and point to that right hand side, right? So this is linear regression, and so there are a whole bunch of other estimators that again don't perform very well, right? And so on the right hand side I have classification. So I'm just again looking at a very simple setting where I have linearly separable data, in the sense that this region is class 0, this region is class 1, very easy to separate it by a linear discriminant. And so here of course I add in some corruption. Do I point out? Yeah, 10% arbitrary corruption. And then you can see that if I use a linear SVM, it's essentially making random guesses, a misclassification error of 0.5. And then interestingly, if I use logistic regression, its error is almost 1. So it seems to be systematically wrong in the opposite direction, right? But of course you wouldn't know that given a corrupted data, right?
So the corruptions are to labels or X's or Y's?
Or to both. To both. So there.
It's not linearly separable anymore.
After the corruption, that's right. That's right. So you can see that, okay, so things are not so good, right? And again, here I have plotted some existing and even recent approaches like torrent that are just a couple of years old that don't seem to be performing so well. So in particular, these are the two issues, which is that the error essentially diverges with the dimension. So in extremely low dimensions, I'm fine, but as the dimensionality grows, things are not so good. Yeah.
The corruptions, is it after you look at the benign samples, you artificially design the corruption, or it is sampled from some bad distribution in your simulation?
So in this case, I didn't select it maliciously. So in the sense that if you force me to, I mean, I guess with a high dimensional, 500 dimensional line, it might still be tricky, but yeah.
Doesn't it seem counterintuitive that you get error 1 all the time?
Yeah.
So this was a particular, I guess, instantiation of Q. But yes, so in general, we would imagine so the failure case to be this. In general, I would in fact even say this is not so bad, so long as you can detect that it's systematically biased in the opposite direction. But in general, it just so turned out to be this way in our.
There's always a logical problem, though, with contaminations, as Huber framed in the original, that in fact the parameter is unidentifiable for fixed epsilon, right? Because if the parameter is the parameter of the central P. So it's not quite, so in this case, where you're doing training sample and test sample, and one was from purely from P and the other one was corrupted.
That's right. That's right. So essentially,
a lot of that was biased.
Right. So essentially, if I have, so the way I'm validating, so of course here actually this was just parameter error where I actually knew theta star. But if I'm looking at prediction error or some empirical estimate of the prediction error, then if I just evaluate the estimator on some test portion, it could be misleading, primarily because the test samples would also be from P epsilon, which would be misleading. But we may still want to ask this question, which is that, can I actually estimate this functional of just P, not P epsilon, with some kind of a priori guarantee?
A priori guarantee depending on epsilon, right? I mean,
depending on epsilon.
An infant sample.
That's right. That's right. So, and so this was essentially the problem posed by Huber. So that's why it's a Huber contamination model, and things are difficult, right? And so let's look at the heavy tail setting. So here again it's just linear regression. I'm just plotting ordinary least squares as well as some regularized L1 and L2 regularized least squares. And then again on the x-axis is the number of samples divided by the number of features, right? And the y-axis is just the parameter error, right? So here things are not so bad. You can see that the parameter error is reducing as the number of samples increases, but it's not getting the sigma square root p by n rate. Okay, so I guess I should have plotted that curve so it's somewhere much lower, right? And so these two plots are just with different noise variances. And so in general, I guess the takeaway from these two plots is that even with large number of samples, so again, large number of samples might suggest that, okay, even with heavy tails, if I see enough samples, things would be fine. But it's still not as good as, for instance, if you would have had nice sub-Gaussian tails. Okay? And so this is, again, depending on a perspective, you may consider this to be a problem, right? So, so what we show is that things are actually much simpler. So we do provide a class of estimators, but they are actually very, very simple. And they actually get rates that are almost optimal under some settings. So let's look at the our estimator. So again, we are in this general risk minimization framework, right? So training and testing all are with respect to risk minimization. So I have some random vector z, right, drawn from distribution P, and then I have some set of feasible parameters theta. So this is a set of feasible parameters, and then I have some loss function that measures the goodness of fit of some model parameter theta to z. And then what I care about is the expectation of this guy with respect to z, right? So I care about this population risk. So I'll keep saying population risk. So this is what you want to minimize, right? But the problem is that nobody gives us p. I'm just going to see samples drawn from p, and of course the implicit assumption is that these samples are representative of the distribution p. And there are two ways in which I'll violate that assumption, where I arbitrarily cut some portion of the samples, or this distribution p has very long tails, so that you may not have very good information about the tails. Right? Okay, so what are some common approaches? So the most common approach, workhorse in statistical estimation, is empirical risk minimization. Right? So what I do there, given essentially an empirical distribution rather than the true distribution, is just substitute in the expectation with respect to the empirical distribution, essentially the empirical risk rather than the population risk, and minimize that guy. Right? So again, this works well only when the set of samples are representative of p. So the caveat is that it lacks robustness. Right? And so because of this, Huber started his robust statistics program, where he essentially suggested that we do M estimation instead of just MLE or regularized MLE, where essentially instead of the loss, the original loss here, which could just be the log likelihood, right, substitute in some surrogate of this loss that's more robust, in the sense that if you minimize it, then the corresponding estimator would be more robust to potential corruptions. So it is more robust than the regularized MLE, definitely, but the thing is that it's not optimally robust if you use convex loss functions. Okay, so to get much better robustness guarantees, you would actually have to look at highly complex surrogate losses that are intractable to optimize. But there have been some other estimators based on tournaments and even depth, including the Chao Gao and others. The earliest was actually proposed by Tukey, who has also studied this problem. But largely these are computationally intractable. And so there seemed to be this computational tractability and I guess robustness trade-off. So you can either get one or the other, but not both. Right? So in fact, Chao's estimator, I think he even showed optimality, but of course it's intractable to compute. Okay, so that was the setting. So now let's revisit risk minimization. Again, this is just risk minimization, this is my population risk, and I want to just minimize this guy, right? So consider this sequence, which is just projected gradient descent, right? So I'm not bringing in samples just yet, right? So if I look at the sequence, again, it's just theta t minus some step size times the gradient of the risk, right? And then projected onto the feasible set. So if R is well behaved, we know that this converges to the true parameter, right? So things are good. The only caveat is that nobody is giving us this guy in red, right? So if I know the form of R, I can actually substitute in gradient of R. But the reason we do not know this is that this is essentially the expectation with respect to P, which we do not know. So that's essentially the caveat, which is that we do not know the true gradient. But this then suggests a very, very simple algorithm, which is that you substitute in some other estimator of the gradient other than the gradient of the empirical risk. Okay? So this is essentially our algorithm in a nutshell. You can think of this as a meta algorithm, which again is just performing projected gradient descent, except that instead of the gradient of the empirical risk, I'm assuming I have access to some other algorithm that computes robust estimates of the gradient. Okay? So in other words, this function g at any given parameter theta t in this case, and some samples, corrupted samples, right, samples from some long tail distribution, and some confidence parameter delta would give me the gradient, a robust estimate of the gradient with that's good, and I'll define what that good means, with confidence at least 1 minus delta, with probability at least 1 minus delta. So that's what I want from this G. But the meta algorithm is pretty simple. It's essentially just projected gradient descent, right? So all the difficulty I've just pushed into estimating robust gradients, right? So the important thing to note is that this is distinct from M estimation. In M estimation, we focus on robust estimates of the loss, and then I look at an empirical expectation of that and minimize that, right? So whereas here it's an algorithmic estimator. Essentially I have a sequence of estimates, and I may want to analyze the sequence of estimates. So this, I would argue, is something that is actually very exciting in some sense, because so imagine that we don't worry about robustness, and I'm just optimizing the empirical risk, like Francis was talking about. So in that case, so just like in Francis' analysis, so I can look at the iterates of my optimization algorithm and say what are the statistical properties. So if I go 5 years back, the standard approach was to look at the statistical properties of the MLE, essentially the regularized MLE, and look at the optimization error, which is how far is this iterate from the global optimum, and then add these two guys up. But this is very, very bad. So adding these two up, in the sense that it's very loose. We can get much tighter results by just treating this iterates as a bona fide estimator, rather than an optimization algorithm targeted to solving some statistical estimation problem. So we in fact have some papers forthcoming where we show that we get very, very tight and excess risk bounds, again using very, very simple analytical tools. But I don't want to talk about those, but essentially this paper is also of that same flavor. We want to look at the sequence of iterates and treat them as a statistical estimator rather than an optimization algorithm solving some other statistical estimation problem. And in this case, there is no statistical estimation problem that this guy is solving. Right, so again, of course, the key issue here is how do I get this robust gradient estimator, right? So here is what we mean by a robust gradient estimator. So at any parameter theta, and given some potentially corrupted samples dn and some confidence parameter delta, I want this guy to be close to the gradient of the population risk at parameter theta. And specifically, the bias is bounded as follows, right? It's essentially some constant alpha, which is a function of both the number of samples and the confidence parameter delta, times and the distance of this theta from theta star.
Yes, who is theta star?
Theta star is the minimizer of the population risk.
But then you wiped away the bias, because now you're computing, I mean, you know, as a statistician, you'd be trying to compute the parameter evaluated at the full population, which is generated.
Oh, that is theta star. So let me see if yeah, so this is theta star. So it is the minimizer, and again, I'm assuming R is well behaved enough that it has a unique optimum and so on.
Right, but for example, if your data came from P rather than
Yeah, so that's the assumption here.
no, because
Because there are many stars.
what?
There are many stars.
Yeah,
It's not identifiable.
No. So here again, I want to clarify the definition of theta star does not involve the Huber contamination.
no, that's right. That's
Right.
perfectly possible.
Yeah,
But then you're not. But that's a different problem. I mean, that's also a problem.
right. So again, so the one worry again, just to paraphrase what you're saying, is that so I'm seeing P epsilon. There could potentially be other P's, each of which might have their own theta star that are epsilon TV distance from P epsilon. So that's one worry, right? But what we show is that under some conditions that I'm going to talk about, right. So how do I? So maybe all of those guys are going to be close enough. So that's the essential upshot.
Then your risk has to show that. That doesn't go away, no matter how many iterations you do or you know.
So
Sample size.
right. So here what we do is that we pick one target, which is this theta star,
Okay.
and then we show that we converge to this
Yes.
up to some constant bias. So essentially, even if there exists some other P prime with a corresponding target, our results essentially show that that corresponding theta star prime would also be close. So it does not matter in that sense. Right. So, right. So this is essentially what we want from a gradient estimator. It's some function alpha times the distance. So essentially this comes up because of the variance of this guy. So essentially if I'm far away from theta star, it will typically, yeah.
In optimization, it's possible to replace the difference between theta star by the gradient of R theta. We have a multiplicative bound.
Is it common?
So why don't you so in optimization you would replace the L2 norm between theta star by the gradient of R at theta, which has a similar flavor.
By the what?
Gradient of R
Uh-huh.
at theta.
Gradient of R at theta. That's what this is.
Yeah, but it's on
On
the right.
the other side, so that it's sort of relative.
Oh, I see. The relative.
Which you have similar behavior, but this is,
I see.
and then you get like trivial bound of for the convergence of the algorithm. It's two lines.
Right. But we needed this actually. So I will talk a little bit more about the role of this alpha. So this alpha, so let's actually see what this is saying. So what this is saying is that this G is actually a biased estimate of this gradient, right? So in general, if I'm going to do, and essentially the core, one of the important theorems is essentially an analysis of bias gradient descent. Now, if my gradients are going to have some systematic bias, they could actually just diverge. So this bias has to be controlled, and essentially with what it boils down to is a condition on this alpha. So if this alpha has to be small enough. So if I give you a gradient estimator where this alpha is extremely large, things are not going to work. And so in our analysis of bias gradient descent, it essentially boils down to control over this alpha. So that's why I stated it in this way. And then I have this additional constant beta. Right. And so, yeah, so just as I mentioned, we essentially want to control this alpha so that the bias of the gradients are not too large, which in turn amounts to a bound on the amount of contamination that's allowed. Because if the contamination is too large, there would be no hope for us to estimate, to get gradients which have a small enough bias. Okay, so that's the setting, right? So we need robust estimates of the gradient. Now the key thing is really that though this sounds complicated, right, it's essentially just a robust mean estimation problem. So if I look at the gradient of the risk, it's essentially the expectation of this gradient of the loss, right? So if Z is a random vector, I can think of the gradient of the loss for given at a particular data point z as another random vector u, and then given samples z1 through zn, I have these samples from this random variable u, u1 through un, right? Of course corrupted, right? So I have these samples, and given samples u1 through un, what I'm asking is to estimate the mean of this random vector u given these n samples. Now in the absence of corruption, what I would do is just estimate the sample mean, right? We have the law of large numbers and a whole bunch of nice theory that says that the sample mean converges to the population mean, but there is an asymptotic efficiency of this, but not finite sample efficiency. So in the presence of long tails, I might not want to, and even if there is no corruption, it's just long tails, I might not want to use the sample mean, right? But of course, if I have Huber contamination, I definitely don't want to use a sample mean, right? So again, this is the setting. I have p epsilon, which is this mixture model, and I receive samples from here, but I actually want to compute the mean of this guy, right? Interestingly, this is just over the last year, there have been a whole bunch of interesting papers that have tackled this specific problem, which is given n samples from some random vector, how do you estimate its mean, right? It's a simple problem, but this is exactly the subroutine that we actually needed, right? So what we do is leverage the estimator of Lai, Rao, and Vempala. Just some very small tweaks, but we just had to do a much finer analysis to get the to actually get the bounds on the bias. So here is the essentially the mean estimator under Huber contamination. So the main problem occurs in, so if I'm going to give you samples where 10% of the samples are corrupted, the main problem occurs in high dimensions. If this was in one dimension, we have a very, very simple estimator that all of us knows, which works really well, which is the median, right? So in 1D, the median is fantastic, right? Unfortunately, in high dimensions, the median is not necessarily optimal. In fact, it is not optimal. So the difficult thing happens in high dimensions. But imagine that I can essentially reduce the problem to one dimension. So I have my sample mean of the corrupted samples, right? And then I look at the direction of this guy from the population mean, right? So I have this direction. If I know this direction, I can just compute the median along this direction, and I can just compute the sample mean along the projection along the orthogonal direction, right? So long as I have this direction, I reduce it to a one-dimensional problem. All the corruption is just in this one-dimensional direction, and that's easy to do, right? The problem, of course, is that I do not know this direction, right? Which is the difference between the corrupted mean, sample mean, and the population mean, right? So how do I get this? I can do this by a recursive step, right? So imagine that given my p dimensional space of p-dimensional space, I can split it into two spaces: a clean subspace where the projection of this direction is small, right, and a bad subspace where it could be potentially large, right? So in the clean subspace, I just use the sample mean, things are good, right? And the corrupted subspace, I just recurse. So this essentially allows us to kind of shoehorn in on the gradient shift direction, right? And so this in turn you can just do using SVD. Okay, so this is the essential high level idea. Most of as to why just doing SVD would help me get the clean subspace, that I wouldn't have time for. Yeah.
Could you also use median of means type estimator?
That's separate. So let me come to that. So that's not for Huber contamination. So if I have Huber contamination where I arbitrarily corrupt 10% of the samples, a median of means would not work. Where median of means would work is in the heavy tail of the model, where I have longer tails. Then here again, I don't want to use a sample mean in spite of the law of large numbers because of its asymptotic efficiency and not finite sample efficiency. What I do want to use, and again these estimators go back to Nemirovsky and others, think this is one of the earlier references, but there could be earlier references. Right? So what it does is actually very simple. It splits your samples into B batches. In each batch, you compute the mean, and you compute the median of these B means. So it's called the median of means estimator. And so this turns out to have much better tails, even when the underlying distribution has bad tails. Okay? So there's been a whole bunch of interesting, even recent analysis that provide much better analysis even in the high dimensional case, and we use essentially one variant of this, which is a geometric median of means. So again, as I said, I split my samples into B blocks, right? Compute the sample mean of the gradient in each of the B blocks, and then just compute the geometric median. Okay, so which essentially is the centroid with respect to the L2 distance. This is it. Okay, so again, a relatively simple estimator, slightly more complicated than just computing the overall sample mean, but in a lot of modern computational infrastructure, the samples are already split into multiple nodes. So here, what is usually done, you compute the gradients in each of these nodes and just add them up. Instead of adding it up, you perform this step. That's it. And as far as the number of blocks B, from our analysis, very, very simply follows. You just set it to roughly log of 1 over delta. So this would then give you a gradient estimator that has controlled bias with probably 1 minus delta. Okay, so let's look at some simulations. Again, the counterparts of the initial plots that I showed, and see how this very simple modification works. So again, let's look at the linear regression model. Again, these are extremely simple setups. The covariates are just standard Gaussian, and then the parameter theta, of course, has large norm, but it's pretty simple. Standard Gaussian noise. And so we again compare the ordinary least squares, some recent estimators, as well as the Huber laws. And I'll just mention one thing, which is, so this was our initial idea, which is that if I am going to reduce things to robust mean estimation, one thought that some of you may have is that why not compute the sufficient statistics robustly, right? So in the ordinary least squares, if you can compute the covariance matrix and the dot product of the covariates with y robustly, then maybe just substitute in these robust variants and see how it plays out. And so that's what we call a plug-in estimator. And so we systematically analyze this guy and show that it doesn't work so well. It doesn't get the optimal rates. And also empirically it doesn't perform so well. So that's that. And so this was a plot that I showed initially. Again, this is for linear regression, parameter error. X-axis is the number of variables. And so this orange curve is our robust GD method. It's not exactly 0, except that these guys are just so large that it seems that it's 0. Yeah.
Seems like you have a very good starting point there, I guess.
You have a very
like in your orange curve there.
orange curve.
It seems like you start. I'm sorry, it's not.
Oh,
like,
yeah.
like I guess the question is like, how do you choose your starting point? Is it?
Oh no, so here this is not iterations.
Yeah,
this is just a problem dimension.
Yeah. I guess how do you choose your starting point?
I think we just started at zeros, and so what we show is that it doesn't matter. Yeah. So again, yeah, we are not. I guess it's not solving some non-convex optimization problem. It's just a sequence, and we show that the sequence has good properties no matter where you start from.
I probably missed it, but what is n here? Why
Number
is
of
the risk,
samples.
No, in this figure, what is n? Why is the risk constant?
So it's not constant. It's just at 10 to the minus something. There is actually an increasing risk. It's just so small compared to these guys.
How is n scaling?
How is n scaling? I forget exactly. I think it was.
It must be in some way in which the optimal risk is constant.
Again, it's not constant. So.
Well, so you're saying that the robust gradient descent is not constant, but I'm asking, like, what is the optimal risk here a constant? N must be maybe proportional to p here.
N must be proportional to p. That's right. That's right. Right. So I forget exactly, but yeah, exactly what the constant is, but yeah. And so here is the parameter error as a function of epsilon, and you can see that parameter error does increase with increasing corruption, which is as you should expect, right? So if I corrupt 90% of the data, I should not be able to estimate any functional of P, right? Primarily because of the non-identifiability, right? So, and this last plot explicitly shows this, where, so these are log of the parameter error against the iterations, right? So all of these guys, again, for up to 30% corruption, right? The parameter is parameter error is reducing, but if I corrupt 40% of the data, it's stuck where it started, right? So there is a ceiling on the amount of corruption I can handle, and so that's what comes up in our analysis as well. And then if I look at classification, again, it's just logistic regression, and my metric now is actually going to be 0-1 classification error, and it's on a held out test set that's clean, not corrupted, because I actually want to validate what its 0-1 error is. And so here, these were the two curves that I showed, and here you can see that our estimator actually gets a much better misclassification error. And you can see that here, again, versus epsilon, it has a much more graceful increase in misclassification error. And then here, again, it shows that the parameter error keeps reducing. Right. So in the heavy-tailed case,
I'm confused.
was there a question?
Yeah,
Yeah.
Theta star doesn't exist for the logistic model.
Theta star does not exist for the logistic model.
Yeah, not if it's separable. The minimizer of the logistic loss on separable data is at plus infinity.
Minimizer.
I mean, the minimizer of the logistic loss
So there may be
over at plus infinity.
some regularization.
It's
in
low
this
dimensional problem, so
It's a low dimensional
with high probability, it's not separable for logistic.
What was
for
N?
logistic regression.
It's a low dimensional,
This
so with
generation
high
looks
probability,
quite
it's not separable. There's a phase
It
transition on
says
the
linearly
dimension
separable.
and the signal to noise ratio.
Right.
Yeah,
Not really sure what
fine,
loss
don't
we
worry about it.
used, but
I don't care.
right, not really sure what loss we used.
I mean, but like,
Yeah.
There is a global,
There is a global minimum, I see.
if the data is not separable.
Right.
I think you're
Right, sure. Yeah, I guess so. Yeah, anyway, so I guess I'll have to think about what loss we used. But these were the curves that we got. So this was for heavy tail. So again, in the interest of time, let's define relative efficiency. Just higher means that the other estimator is worse. And so here, this is our curve. And you can see that it's much better, right? So here is another kind of toy experiment that we did. This is a case where the model is not actually true. So here I have an image, and I'm assuming that each of the pixel intensities is a sample drawn from a linear regression model where the covariates are drawn from some eigenfaces. So clearly the underlying model is not true, right? And then, so this is the true image. This is the best possible reconstruction given the basis, right? And so this is the corrupted image, right? So given some occlusions, so here the occlusions are just pixel intensity 0, but you can imagine that I draw the corrupted pixel intensities from some other distribution to confuse, right? And so this is our estimator, right? So even in this case where the model is clearly not true, it seems to be doing okay. And so this is, I think, OLS, and this is a recently proposed estimator. Okay? So again, it's just a toy experiment that we did just to see how it does. So let me go to the theorem in the short time that I have. So, so I just assume strong convexity of the population risk as well as strong smoothness, right? Lower bound and upper bound by a quadratic. So in the case where this bias statement does not hold uniformly over my feasible set, I would need to do sample splitting. So this is just a facet of our analysis where given these n samples, I assume that each call to this gradient estimator is given a fresh batch of samples. I do not need to do this if this holds uniformly over theta, right? But given that our theorem holds for any gradient estimator, we just stated that. So if you see n twiddle and delta twiddle, it's essentially the batch size. Okay. Again, if it's a uniform oracle, then gradient estimator n twiddle is just equal to n. So here is a key assumption we have on the bias of the estimator, right? So the alpha again came from the expression for the bias. We say that the gradient estimator is stable if this alpha is strictly less than the strong convexity constant. If this holds, then the bias is small enough and the robust gradient estimator does not diverge. Okay. We haven't shown the if and only if, but I think one can show with a little bit of an effort. So given this condition, this is essentially the contraction parameter that we define. Under this condition, you can see that this is less than 1. Okay. So again, it just depends on the strong convexity and strong smoothness constants, the step size of the gradient, projected gradient descent, robust gradient descent, and alpha. And so this is our main theorem, which says that if you do this robust gradient descent, then at again with constant step size, then theta hat t, the iterative time t, its L2 error converges to 0 exponentially fast modulo this constant error that scales as beta. Okay, so this holds for any gradient estimator. So given any gradient estimator, you just have to verify, and for this particular statistical model of your choice, whether the gradient estimator is stable, by which I mean that alpha should be less than the corresponding strong convexity constant of the population risk. And you have to derive what beta is, because that specifies your rate. Okay, so let's look at linear regression model. Again, I'm not assuming much about the covariates. So this is the bound that we get. Okay, so theta hat t minus theta star again converges linearly modulo this thing, which has this term sigma and square root epsilon, which is optimal. What is not optimal is, and even this maybe square root of the spectral norm of sigma, capital sigma, what is not optimal is the square root log p. So that's something that we believe is because of this gradient estimator. Potentially with much better gradient estimators you can get rid of it, right? With Chow's Tukey depth, I don't think he has a square root log p, right? But the square root epsilon constant, in case you are disappointed with this, is inevitable. Okay. So
Sample size is implicit in the quality of your gradient estimator.
that's right. So here
Kappa-ish.
it's right. So it's props up in this alpha, which is where it comes up. But it just depends, essentially. So the more samples you have, the better is this kappa. So the convergence rate will be faster. So it should be kappa n, but that's where it comes up. Right. And so I would prefer the sample size to come here, right? But the problem is that this is a constant offset, right? So if I do not have any corruption, so this would just not be there, right? So if epsilon is 0, I would just not have this. And this is also not converging to 0 at any rate, right? I would like there to be an n here, but there isn't. And then I can also look at this in the heavy-tailed case, where I do get the square root p over n, but this is the rate that you actually want in the heavy-tailed case, but of course there is no corruption. So in the logistic regression case, this is again the model that I have. This is the rate that we get, which is slightly worse. So again, I have theta hat t converging linearly to theta star, plus this constant offset, right, which has the square root epsilon, and then this additional term that just comes up because of our analysis in the Huber gradient estimator. But this again, though you see the n, this is something we are not satisfied with, right? But again, given that this is constant, this is not, we didn't spend too much time in getting rid of that. But this again could just be a facet of the gradient estimator that we used, but also potentially our
You
analysis.
don't need to make that constant. You could reparameterize. In fact, there's a whole theory where when rates, if you want, were 1 over root n, there's a theory by which if you plug in the contamination itself, also to be of order 1 over root n, everything works out very nicely because you get a variance and you get a mean squared error. And you can do the variance, a variational calculation explicitly. And you could presumably do that here too, where the rates are not necessarily more than 1 over root n. They have them balanced.
Right. Yeah, so that's actually an interesting point, which is that if I allow this guy to actually decay with n, which is maybe not that unreasonable an assumption, it's easy for me to corrupt 10% of 100 samples. It's difficult for me to corrupt 10% of 10 billion samples. So maybe that could be I would expect it to decay with n. So that's actually, that's a good...
Well, actually, we can show that in fact if things are not going like 1 over root n, if they're going more slowly, right? Then, if you want, you can construct a goodness of fit test, which can tell you that your sample is, at least can tell you that your sample is not coming from your model.
Yeah. So having, so that would be, I think, a good next step to analyze that case, definitely. Yeah. Okay, so I think I'm a little bit out of time. So here are some limitations. So the dimension dependence. So essentially, there is this constant offset, which is the square root epsilon, which is again unavoidable. But then there's a square root log p, which could be gotten rid of. And then there is also a maximum allowed contamination, which essentially depends on data dependent constants. So I didn't spend much time on this. It really depends on the alpha that we got, right? So which in turn depends on constants that are data dependent. So it's likely not optimal here, right? So I think it would be good to also improve that. But in practice, this seemed to be large enough that, so things like 40% corruption of the data, if 40% of the data is arbitrarily corrupted, you have other issues, right? So this anyway is a summary. It's just based on a very small shift in perspective. So we get essentially what are very simple estimators, not anything too complicated, and computationally tractable and scalable, right? So instead of robust estimates of the risk, we're just using robust estimates of the gradient. From a technical analysis, all we need to do was essentially have a much finer analysis of biased gradient descent, trying to see how this bias depends on the gradient estimator that you have, and also when is this benign enough and things won't diverge. But that was it. As far as the algorithm is concerned, it was pretty simple. Essentially, you can just embed these guys into a simple iterative algorithm, and even from a conceptual standpoint, estimating robust gradients is just equivalent to estimating robust means. If you can solve this general problem of estimating robust means robustly, you solve the problem of estimating gradients robustly. So really, that's the larger problem which many people have started to think about. So in some sense, the problem is actually, it's good news in many ways. So yeah, it's computationally tractable and scalable, and it also gets very, very strong guarantees. Okay, thanks.
I think there was a paper by Tukey and Miran. I don't know whether you've seen it. Tukey and Miran that was doing exactly the same thing. And they are not based on estimation. They were using median of means, but they are not based on estimation of gradient.
It's
non-recursive method,
right?
And they obtain results with optimal rates even in the sparse case.
Right. Right.
For linear regression, as you showed.
Right.
So you should compare with their paper.
Right.
It was 1 year ago.
Right. Right. So we only compare to practical estimators. So for instance,
it was practical.
It was practical.
Realizable in polynomial time.
I
It's
see.
very fast.
Very fast. Okay. So I know that there are some estimators that, again, for instance, in the heavy tail case, estimate the, I guess, the empirical risk efficiently or more robustly using things like median or means. But yeah. Right.
Actually, they don't use the recursive method, it is non-recursive, so they don't depend on the initial approximation.
But median of means is only for the heavy tail, not Huber contamination. So, but definitely for the heavy tailed one, we will compare with the others.
So I find the median and mean slightly counterintuitive, depending on how big the block size is, I guess. If the block sizes are too big, then those means are going to be
Corrupted as well.
corrupted.
That's
I mean, why? So I guess either a question, how big, I mean, it's a median if the blocks are 1. So are the blocks really small, so really it looks like a median? Or are the blocks really big, in which case why not use a median of medians or something more robust?
The problem is that in high dimensions, medians are not good. That's really the crux of it. So even when I split it into blocks, I'm still looking at estimating the mean. But the other thing is that even in a heavy-tailed case, I don't necessarily want to use a median. So I guess I've been talking about two robustness cases, one the Huber contamination and the other which is the heavy-tailed case. In the Huber contamination, median is good. In the heavy-tailed case, I don't necessarily want to use medians. But I agree with you. So that when it first came up, and when I first looked at it, I had the same reaction, which is that this shouldn't necessarily work. At a high level, the reason it works, so this wouldn't work in purposefully malicious corruptions, where I can target all my corruptions into a single block. Then you would be in trouble. But if here, the Huber contamination model is in some sense okay, because each sample is essentially, it's a mixture model. It's only, for each sample I'm going to flip a coin with bias epsilon and then decide if it's going to be corrupted or not. And so that's why in any given block there aren't going to be too many corruptions. And so that's,
How big is the block?
so that depends on the confidence that you want your, and again, this is not for Huber contamination actually, so even I'm getting mixed up. So this is for heavy tails. So you don't want to do this for Huber contamination. Huber contamination, we are doing a recursive thing. So the median of means is not going to work for Huber contamination. Yeah, so even I got mixed up, I'm sorry. Yeah, so it's for the heavy tail case where there is no corruption. It's just that the tails are heavy.
Yeah, it's a very basic question. You say that for the Huber contamination, the median works, but
In 1D, yes.
yeah, let's say in 1D.
Yeah.
This is only if the noise is symmetric. Because what do you mean it works? It works for the estimation of the mean.
That's because that's right.
That's right.
But
So
that works only, it's quite a strong assumption, I think. To say
That's
that,
right. So that's right. So for an arbitrary one-dimensional problem, one-dimensional random variable, is the median going to work? Yes. So
because you are estimating the median with this bias due to the contamination, but then the median you don't know if you don't want to make strong assumptions about the noise.
That's
you
right.
don't know how far the median is from the.
That's right. So there is an assumption of symmetric. You're right. That's right. But there are other estimators in the 1D case for robust estimation of the mean.
Yes.
Right. But you're right. So if for some really non-symmetric case, the median is tricky. Yes, you're right. Yeah.
But then does this kind of method, does it work for quantile regression, quantile linear regression, like median linear regression?
So
Does it actually make more sense to do this for median regression?
I think the estimator that we had there, so in the 1D case, I don't think we use median. So we don't actually assume anything about the underlying covariates. So all the gradients. So remember that in our case, we didn't want to make strong assumptions on the gradients, right? Because so I want to say that it's Gaussian, for instance, right? So, but you're right. So for the 1D case, I'll have to see what we exactly used, But yeah,
There's an issue with regression also. I mean, if you assume linear,
right,
conditional expectation to be linear,
right,
and the residual, the x minus the conditional expectation, or the y minus the conditional expectation, to be IID, then indeed you're just as in the symmetric, you're like in the symmetric case for the not other than for the constant. In which
Right.
case you're trouble anyway.
Right.
But if in fact, as is often the case, the y minus the conditional expectation depends itself on the covariance, then you're in the same. I mean, as I said, you're estimating something else.
That's
You're
right.
estimating a function
Right.
which is not the function.
That's right. But again, given some, essentially the question we are asking is that I have some random variable, one-dimensional, and I want to estimate its mean robustly. This is, I think, a solved problem. So I just said median because it's easy for us to.
Well, it's all in the question of how you define things.
That's right.
What does robustness mean?
Right.
All right. Well, why don't we leave it at that for now? We can talk one-on-one after this thing.